Hello and welcome to 4.1 Antidifferentiation. Antidifferentiation is the process of differentiation in reverse. So let's say we had a function, and the function is f of x equals 2x. And we want to take the antiderivative of this function. So what function would we end up with? I'll call it capital F of x. So if we take the antiderivative, so the derivative of x squared would be 2x, correct? So we just took the antiderivative. Now, if I had a function, let's say capital F of x, and I had x squared plus 1, and I took the derivative of this, would I still get 2x? Yes, right? I'll take the derivative of x squared is 2x, derivative of a constant is 0. Let's say, can I come up with another capital F of x whose derivative is 2x? Yeah, like let's say I had x squared minus 4. Right? Derivative of this would be 2x. Derivative of minus 4 is a constant, so 0. Okay, so in general then, anytime I have the antiderivative, when I go to express it, I want to say what it would be. So antiderivative of 2x would be x squared, and then I would attach a plus c to it, and the plus c is a constant. So notice how I could attach any constant. I could have a plus 1, I could have minus 4, I could have a plus 10 or a minus 19, but end result is when I take the derivative, I get 2x, and the derivative of the constant goes away. Okay. And we call that constant c the constant of integration. Okay, so one thing I want to introduce to you guys is this symbol when we take the antiderivative. Okay, the symbol to tell us to take the antiderivative is this, it's almost like an elongated S. We call this the integral sign. We say integral for short. So if I said integral of f of x dx, that tells me that f of x is my, what we call the integrand, and the dx, this symbol tells me the variable that I will be integrating with respect to. So we can say the variable of integration. Okay, so another name for antidifferentiation would be integration. Okay, so we can say aka integration. Okay. So let's take a look at some what we call indefinite integrals. And what we're doing is we're finding antiderivative of each integral. Okay, so for a, we have the integral of 8 dx. So that means we would have, the only way we'll get that is if we have 8x, and then we would put plus c. Okay, for part b, integral of 3x squared. So when we integrate this, what do we get? the only way we would get 3x squared is if we started with x cubed plus c. Okay, integral of e to the x, well, derivative of e to the x is e to the x. This will be e to the x plus c. And an integral of 1 over x dx, well, we should recognize 1 over x. That's just ln of x. So we say ln of x plus c. Okay. So here are some rules for antidifferentiation. We have the constant rule, power rule, the natural logarithm rule, and the exponential rule for base e. Okay, so let's take the, let's use the power rule of antidifferentiation. This is a very classic rule. Okay, so tells us to, when we integrate, we're going to add a power to our exponent, and then we're going to be dividing by that same power, or multiplying by 1 over that power. Okay, as long as n is not -1. So for the first one here in example 3, when we integrate x to the 7, we're going to be adding 1 to the 7, so 8, and then we're going to be dividing by 8 plus c. Okay, if you want to rewrite in a slightly different way, you could say that this is 1/8 x to the 8th plus c. Alright, part B, integral of x to the 99. So that means we add a power, add 1 to the exponent, so x to the 100, and we divide by 100 plus c. In other words, this would be 1 over 100, x to the 100th plus c. Okay, letter C. Now, another way to do letter C, we express the square root as an exponent. So we would have, this would be x to the 1/2 power. Okay, so that means when we go to integrate, we're going to add a power. So if we add 1, if we have 1/2 plus 1, well, 1/2 plus 1 would be what? 1/2 plus 2/2, which would be 3/2. So it's x to the 3/2 divided by 3/2. Now when we divide by a fraction, that's the same as multiplying by its reciprocal. So that would be 2/3 x to the 3/2 plus c. Okay, and then part D, let's express, we have 1 over x to the 3rd, so let's express that as x to the -3. So that means we will add 1, so -3 plus 1 will be -2, and we divide by that same power. So in other words, another way to rewrite this would be, well, we would have -1/2 times x to the -2. Bring that down as well. And then just simplify it like this and say this is -1 over 2x squared plus c. Let's take a look at the next theorem. Some other properties. If we have a constant factor, we could move that constant to the front. So if we have a constant multiplying our function, we can move that constant to the front of the integral, and then we would continue with our integration. If we have a sum or difference of functions in our integrand, we could evaluate the sum or the difference of those separate functions. Okay, so that comes to light here in this next example. So for this one, if we have this polynomial, we could say that this could be split up by doing this. Integral of 3x to the 5th dx plus integral of 7x squared dx plus integral of 8 dx. Okay, and then we would integrate each one. Okay, so for example, if we have the constant here, the 3, the coefficient, we could pull out and then integrate x to the 5th. And then here the 7 we could pull out. And we could easily integrate the 8. Okay, so when we integrate, we'll have 3 times. Now when we integrate x to the 5th, it becomes x to the 6th over 6. Over here we have 7 times. Integrate x squared, that'll be x to the 3rd over 3. Integrating 8 would be just 8x. And then we would attach a plus c. Okay, simplify it a little bit. This will be 3 over 6, which would reduce to 1/2. So 1/2 x to the 6th plus, this will be 7/3 x cubed plus 8x plus c. Okay, for the next part, it'll be easiest to just divide each of the terms in the numerator by x. Okay, so we would have 4 over x plus 3x over x plus 2x to the 4th over x dx. Okay, so reduce as much as you can. So we have 4 over x plus, x's cancel here, so 3 plus 2x cubed. Okay, so next we'll integrate each of these. So here this would be 4 over x. So this would be, when we integrate, 4 times ln of x plus 3x plus, and then we would increase by 4, so it would be 2 over 4 plus c. So 4 ln x plus 3x reduced to 2 in the 4, so that's 1/2 x to the 4th plus c. Okay, next it says we have to find a function f such that the derivative of f of x equals 2x plus 3 and f of 1 equals -2. So we want to get the integral in such a way that f of 1 equals -2. Okay. So if they give us the derivative here, we can take the integral and get the antiderivative. So let's do that. So we're going to take the integral of 2x plus 3 with respect to x. So if we integrate 2x, that's x squared. Integrating 3, it gives us 3x plus c. So now here's our function. Now one thing they told us is this initial condition. They gave us a condition here. F of 1 has to equal -2. Okay, so that means when we plug 1 in to x, our outcome is -2. Okay, so that means we'd have -2 here. We put 1 here and 1 here. And then working backwards, we could solve for c. Okay, so we have -2 equals 1 squared is 1. 3 times 1 is 3 plus c. -2 equals 4 plus c. Subtract 4 both sides. So c equals -6. That means our function then would become f of x equals, and we're just going to replace what the c is. So f of x equals x squared plus 3x minus 6. And that would be our original function. Let's take a look at this example. So one of the things we learned about earlier is how distance is related to velocity, which is related to acceleration. So we saw the derivative of a distance function is velocity. Therefore, if we're given a velocity function, we could take the antiderivative and we could come up with a distance function. Okay, so if information about the distance of an object at some time is known, then that gives us an initial condition. Okay, so let's take a look at this problem. It says a rock is thrown directly upward with an initial velocity of 50 feet per second from an initial height of 10 feet. The velocity of this rock is modeled by the function, okay, v of t equals -32t plus 50, where t is in seconds, v is in feet per second, and t equals 0 represents the moment the rock is released. Determine a distance function h as a function of time. In this case, distance is the same as height. Be sure to consider the fact that at t equals 0, the rock is 10 feet above the ground. Okay, and then part B, determine the height and the velocity of the rock after 3 seconds. Okay, so since distance is the antiderivative of velocity, I'm going to set and figure out the antiderivative of my velocity. And this is in terms of t, so this is dt. Okay, so that means when we integrate this, this will give me, let's see, I would have t squared. Okay, so I have -32 t squared over 2 plus okay, so this gives us -16 t squared plus 50 t plus c. Now they gave us an initial condition actually, right? In this last piece in part A, it says be sure to consider the fact that at t equals 0, the rock is 10 feet above the ground. they also told us that initial height, so initial height of 10 feet. So that basically tells us that we have this scenario. When t is 0, the height is 10, right? So let's plug in 0 in here. That'll give us what c is. Okay, so we have negative 16 times 0 plus 50 times 0 plus c, and this equals 10. Okay, so that means this is gone, this is gone, we're left with c equals 10. Okay, so that means we have the function then. Right, we have the h function. Let's say h of t equals negative 16 t squared plus 50 t plus 10. And then they said, find the height and the velocity of the rock after 3 seconds. Okay, we can do that. So this is part B. Okay, so to find the height after 3 seconds, we plug in 3 into t. So that gives us, we do all this math, negative 16 times 9 plus 150 plus 10 was that negative 144 plus 160. So that gives us 16 feet. So 3 seconds in, the height is 16 feet. And then they want also to know the velocity. Right? They said find the height and the velocity. So the velocity would be v of 3. So we plug in 3 into our original velocity equation. Alright, so negative 32 times 3 plus 50. Okay, so that's negative 96 plus 50, so that's negative 46 feet per second. Okay, so we know it's 16 feet above the ground. The negative velocity implies that the rock is moving downwards. Okay, so when you see the negative velocity, that implies it's going to be coming downwards at that point. Okay, let's take a look at this next problem. Life sciences, change in population. The rate of change of the population of Phoenix, Arizona is modeled by the exponential function p prime of t equals 11.7 times e to the 0.06026 t power, where t is the number of years since 1960, and p prime of t is in thousands of people per year. In 1980, Phoenix had a population of 790,000. So that's like an initial condition. They're telling us a fact in the beginning of the problem. Find the population model P of t. Okay, so we know the derivative already. So we have to take the integral of this, right? Integrate it. So to get P of t, we're going to integrate 11.7 e to the 0.026 t. Okay, so now when we do this, when we integrate, we're going to have to divide by the 0.026, right? Because any e to the 0.06026t would have to multiply by the derivative of 0.026. So that means we have to divide by 0.026t. Okay, so we would end up with that plus c. Now if we divide 11.7 by 0.026, I did this ahead of time, so that gave me 450 e to the 0.026t plus c. Now to get a better function, we don't want the plus c, they gave us an initial condition. In 1980, population is 790,000. Okay, so basically we have an ordered pair there. Now it says that t is the number of years since 1960. So 1980 is 20 years since 1960, correct? And then they say that p prime of t is in thousands of people per year. So that means 790,000 is just 790. Okay, so that tells us this, that 790 would equal 450 e to the 0.026 times 20 plus c. Okay, I did this already, so I had 790, or figure this out on the calculator. So that gives us 756.9 plus c. Subtract 756.9 from both sides, so c equals 33.1. Okay, so p of t then equals 450 e to the 0.026t plus 33.1. And then for the next part, they wanted estimate the population of Phoenix in 2012. So 2012, since 1960, that would be 52. So that means t equals 52. Alright, so I'm going to figure out what's p of 52. Alright, so I'll plug in 52 for my t. 450 times e to the 0.026 times 52 power plus 33.1. Okay, and if you do this, you'll get 1772. And this was in thousands, so I just gotta tack on 3 zeros. So estimated population in 2012 for Phoenix would be 1,772,000 people. Okay, 4.2. So in this section we talk about antiderivatives as areas. Okay, so we start off with some basic area problems, but in terms of some common things that we could easily calculate. For example, a vehicle travels at 50 miles per hour for 2 hours. How far has the vehicle traveled? So if it's 50 miles per hour, our velocity function would be $50. So if we had a graph of it, 50 would be this. Okay, and if we're looking for 2 hours, at 2 hours we would find out it would be this rectangle, and we could take the area of this rectangle, which will be 2 times 50. How far has the vehicle traveled? It would have traveled 100 miles. Okay. Business total cost as area. Greenleaf Skateboard determines that for the first 50 skateboards purchased, its cost is $40 per skateboard. What is the total cost to produce 50 skateboards? Okay, so that tells us that it's $40 per skateboard. Okay, and if there's 40, that would be this horizontal line going across the top. And there's 50 skateboards, so it would be 50 times 40. So that means that would be a total of 2,000 skateboards. Example 3, distance as area. Says the velocity of a moving object is given by the function v of x equals 3x, where x is in hours and v is in miles per hour. Use geometry to find the area under the graph, which is the distance the object has traveled. So we're going to find out for the first 3 hours. Okay, so if v of x equals 3x, so if it's a triangle now, remember area of a triangle is 1/2 base times height. We have the base, which will be 3. The height, well, we could figure out this height if we plug in 3. The height is 9. So we have triangle where the base is 3, the height is 9. So area is going to be 1/2 3 times 9, which will be 27/2, right? Now 27/2, that's what, 13.5, 13.5. Okay, so we have 13.5. Now for the second part, says between the 3rd hour and the 5th hour. Let's do that in a different color. So they want between here and here. So for this shape, this is a trapezoid, but we could break it up into 2 shapes that we are familiar with, a rectangle and a triangle. Okay, so Okay, so we know the width here is going to be 2. So remember, for a rectangle, this area is base times height. Right? For a triangle, we'll still do 1/2 base times height. So for the height up to here, well, this was 9 up to here, correct? So this is still 9. And then we got to figure out this remaining height over here. Okay, so when we plug in 5 into the function, it's 15. So up to here is 15, up to here was 9, so this has got to be, this is 6, and this is still 2. Okay, so that means to get the area, we would do 2 times 9, that would give us the area of this rectangle. So 2 times 9 plus 1/2 of 2 times 6. So that would be 18 plus 6, which will be 24. So that would be 24, and this was what, miles? Miles. So for the first 3 hours, it was 13.5 miles. And then between hours 3 and 5, 24 miles. Okay, so it brings us to this discussion on Riemann sums, Riemann summation. So a lot of times what we do is to estimate the area under the curve. Right now, the area we did up until now, these were shapes that we could easily figure out the area of. We figure out area of a rectangle, area of a triangle, and area of a trapezoid, which we broke up into a rectangle and a triangle. So now what happens if it's a curve that we can't easily break up? Well, we use rectangles. Okay, rectangles are used to approximate the area under the graph of a continuous function. Okay, it's not a perfect setup. You see here under this curve and this graph, there's missing, there's little gaps, right? There's this little area piece here that we're not accounting for. There's a little overestimate here, right? I mean, it's not a perfect setup. Another overestimate over here for this one. And then this one falls short. This one's an underestimate here. So it's not a perfect setup. Now, if we were to put more rectangles, perhaps, that would give us a closer approximation. Okay, so notice the word approximate. We're just using the rectangles to get an approximate area under the curve. Okay, so we take the area of each rectangle, we calculate the area of each rectangle, and then we take the rectangles and we add up the areas. So we add the area of the first rectangle with the second, the third, and with the fourth. We add up all the areas together, and that gives us the area underneath the curve, if you will. Okay, so for these 4 rectangles, we would come up with, well, the first thing we come up with is we would figure out the width of each rectangle, right? And the width of each rectangle would depend on this region, right? Now, a lot of times they'll tell us the boundaries where we're starting and ending. They'll say between A to B, we want to divide the region into 4 subintervals, or 4 rectangles. So to figure out the width of each rectangle, we take and subtract b minus a, and then we would divide by 4. That would give us the width of each rectangle. So this introduces us to this sigma notation that we have down here. The sigma notation will help us to write the sum in a shorthand notation. So this tells us that we're starting I equal to 1, going up to 4. And this one says to find the sum of the product f of xi times delta x from I equals 1 to I equals 4. Okay, and that'll basically be a shorthand way of writing this notation. Okay, so in the next video, we will show how to practice some sigma notation, so we get a feel for how we can evaluate these summations. Okay.